My name is Amy Zhu, and today I would like to present how we jointly optimize the design and fabrication plans for the carpentry domain. This work was done in collaboration with Haisen Zhao, Max Wilsey, Chandrakona Nandi, Zachary Tatlock, Justin Solomon, and Adriana Schultz. Fabrication-oriented design has attracted dramatic interest in both the manufacturing industry and the graphics domain. The vast majority of existing works search over a design space, assuming that there is a unique way to fabricate each design. These works optimize assuming that there is a bijection from each point in the search space to a fabrication plan. However, this is not always true. In many cases, you have multiple ways to fabricate a design, and this matters when we are doing optimization. Imagine, for example, that you want to fabricate this chair. There are a huge variety of interesting ways to fabricate it, and here are two examples. Each fabrication plan is visualized with its parts packed onto carpentry stock pieces. We define a fabrication plan as a cutting plan. Cutting orders and cutting tools are indicated by numbers and colored dots. The first plan uses less material, but the second will minimize fabrication time since it has a lot of repeated cuts. In general, each plan makes a trade-off between multiple conflicting objectives that we might care about. Users therefore want to understand the landscape of possible compromises that we can have with each fabrication plan. Note that there are a set of plans that are optimal according to this multi-objective optimization problem. They lie in what is called the Pareto-optimal frontier. So how can we find this set of optimal fabrication plans given a design? In our prior work, called the Carpentry compiler, we address this with the fundamental insight that both design and fabrication plans are programs. Note that a design is a sequence of instructions that builds a geometry bottom-up, and fabrication is a sequence of physical operations that construct a shape. So we can use compiler techniques to do this optimization. However, this is only useful if you have a design and you're trying to find an optimal way to fabricate it. But what if you want to optimize the design itself? In general, when experts want to optimize fabrication, they will also consider variations of a given design. For example, consider this model and one of its Pareto-optimal fabrication plans. We can generate design variations by discretely varying the joints of the input design. Now we are able to get a fabrication plan that is 80% faster to manufacture and one that reduces material costs by 15%. As you can see, the first design variation produces 4 identical parts, which can be fabricated with one single cut. The second design variation produces 2 long and short parts, which can be packed into just 2 pieces of stock, which is impossible for the input design. In this work, we propose a novel approach that allows users to consider the space of possible design variations when optimizing for fabrication plans. Each design variation comes with its own landscape of fabrication plans with different cost trade-offs. Here we have a Pareto front made from the points of 6 designs, and different fabrication plans on the Pareto front may also come from the same design variation. Our goal is to search all possible design variants to find a Pareto front that minimizes fabrication costs, where each Pareto optimal solution is a pair of design and fabrication plan. Designers must therefore explore the joint space of design and fabrication plans, but such co-optimization is very challenging. We would like to search over all designs and all fabrication plans together. Unfortunately, this joint space does not explicitly exist. The space of all fabrication plans is only implicitly defined by the designs. That means that for each design, we have a completely different fabrication space we must search through. Searching the space requires an inner loop, an optimization inside an optimization. This nested loop is the definition of bi-level optimization problems, where the constraint region of the upper level problem is implicitly determined by the lower level optimization problem. But what if we tried to brute force the problem as formulated with 2 nested loops? Turns out running Carpentry compiler in this way is not feasible. The chair model takes 8 to 10 minutes to explore a single design variation. It would take more than 10,000 hours to explore all design variations. In this work, we address this challenge with 2 technical contributions. One is a new data structure to compactly represent this large combinatorial space of variations. The second is a novel search algorithm to enable efficient multi-objective optimization over this data structure. So let's start with the data structure. Our key insight is that our search space is full of equivalent substructures. In particular, design variations may have subsets of parts in common within a single design variation and across different variations, and these have the same fabrication plan space. Exploiting these equivalences can help us create a compact representation. To do so, we will use a data structure called an equivalence graph, or egraph for short, which comes from the programming languages community and compactly and efficiently represents many equivalent programs. The basic idea of an egraph is that each program is a node represented with a solid line. Here we have the programs A and 2. Each program is its own enode. Note the dashed box surrounding each enode. These represent equivalence classes or E-classes, which store all equivalent programs. Right now, A and 2 are not equivalent in general, so they are in separate E-classes. Now, what happens if we want to represent the programs A plus A and A times 2? Notice that these two expressions are equivalent, so they belong in the same E-class. Also note that when we added arrows to the node's children, we pointed to the E-class rather than a specific E node. Why is this helpful? Well, now imagine that we add this new operator, plus, which points to these two E-classes. Note that with the addition of one new E node in E-class, we are representing two new expressions. So the idea of an E-graph seems very promising because we think that different designs will have shared parts. But how will we adapt them for a problem domain? First, we need to encode different design variations in the E-graph. Second, we need to encode fabrication plans into the same E-graph. Our solution to this is to use a bag of parts representation. Every design is represented as a bag of parts only, with no information about assembly. So let's concretize this notion into an E-graph. Each design corresponds to the E-class that produces all of the parts that it needs. Two designs or sub-designs are represented by the same E-class if they use the same bag of parts. So an E-class has a collection of parts. How do we encode a fabrication plan? We do it as an E-node, which is inside some E-class. An E-node is then a fabrication plan for all of the parts in its E-class's bag of parts. A node can either be atomic, representing a packing of parts onto a single piece of stock, or it can be a union node, combining multiple other E-nodes and fabricating all of their parts. Notice how some parts and their subsequent fabrication plans are referenced across many designs. With E-classes and E-nodes defined, we say that two E-nodes are equivalent and belong in the same E-class if they generate a fabrication plan for the same bag of parts. So for example, these plans are all equivalent, even though they may use different kinds of stock or different quantities of stock. Because we use the bag of parts as equivalents, we call our data structure the bag of parts, or BOP E-graph. Let's walk through the process of generating an E-graph for an object. Consider this design and its fabrication plan. Each set of packed parts generates its own leaf node, called an atomic node. We then traverse the E-graph, generating union nodes, which represent a fabrication plan for all parts in the child plans. Now each unique bag of parts becomes its own E-class. We can continue to add more fabrication plans for the existing design variation, and we can also add new design variations. Once we take the fabrication plan and add it to the E-graph, an E-class with the correct bag of parts will be created. The E-classes E1 and E2 correspond to the two designs, encoding all possible ways to fabricate their bag of parts. E4 captures ways to arrange the Y and Z parts which the variants share. And the second design variant also captures the union of an E-class with itself. E-class E5 reuses the arrangement in E-class E9. Now we have a way to exploit equivalence. We need to figure out how to efficiently explore the E-graph to discover the Pareto frontier of optimal programs. The typical optimization technique for an E-graph has a two-stage approach. First, we construct an E-graph with all possible equivalent programs. We call this expansion. Then we extract the optimal program by minimizing some cost function. We call this extraction. Even with bag of parts E-graphs, the combinatorial nature of fabrication plans means that the graph would grow too big for memory in expansion, and extraction would take a very long time. We want to find an iterative solution that will help us mitigate this obstacle and help us only grow the E-graph towards good design and fabrication plans. In our work, we instead propose a feedback-directed extraction method called Iterative Contraction and Expansion on E-graphs, or ICEE. ICEE is an iterative extraction method. First, we extract current optimal solutions from the E-graph. This gives us feedback about which E-classes are valuable. Second, we use this information to contract the E-graph. Third, we use this information to grow the E-graph in a focused way, moving us towards more optimal fabrication plans. So let's take a more in-depth look. ICEE takes a feasible design space D as input. The initialization step selects a small subset of design variants from D and a small number of fabrication arrangements and adds them to the E-graph. ICEE then applies a genetic algorithm for multi-objective optimization to generate a Pareto front from the current BOP E-graph. The resulting Pareto front is used to compute ranking scores for each class in the E-graph. The ranking score measures two counteracting criteria. One is the exploration, or how many fabrication variants of all theoretical variations have been explored for this BOP. The other is impact, or how often this BOP is used in Pareto-optimal solutions. We then contract by identifying low-scoring E-classes and removing them and their parent E-nodes to get a compressed BOPE graph. And this contracted BOPE graph is then further expanded. Ranking scores are used to guide generation of new design variations and new fabrication plans for existing E-classes. The algorithm exits the loop when the termination conditions are reached, returning the final Pareto front. Now we have proposed the BOPE graph and the ICEE algorithm to co-optimize design and fabrication plans. Let me show you some results. We evaluated our approach on a variety of models, some needing only sequential cuts on lumber, and where others required 2D partitioning of sheets. We found that exploring the space of design variations meant finding much lower minimum costs in the Pareto front, greatly improving our ability to make new trade-offs. For example, imagine that Alice is making a number of reclaimed wood dressers to furnish her new house, but has left it to the last minute. She values completing this project quickly above all else. The fastest fabrication plan with her original design would take about 36 minutes to cut with setup and measurement. But through design exploration, we find a design with an optimal fabrication plan taking 15 minutes, which is a 58% time savings. In fact, when it comes to minimizing time, 4 models save between 20 to 30%, 3 between 30 to 35%, and 2 models save between 50 to 60%. Similarly, imagine that Bob has been asked to make a number of bookshelves for a nonprofit and has a strict budget to use the least amount of material possible. Bob can take as much time as he wants to make them, but must minimize the material costs. His initial design produced a minimum material cost fabrication plan that used $40 worth of material. It is usually difficult to save on material, but by modifying the bookcase design to break up the long side edges, we can pack the smaller parts into $30 worth of material. In terms of material, we also save 7% in the loom, 7% in the jungle gym, and 15% in the frame. Though these improvements might appear small, they amount to big cost savings over big projects. For the hobbyist or professional who values precision and the quality of the final product above all else, design exploration can help here too. For 4 models, we find solutions that reduce error by 62 to 82%. We conclude that design variations have the potential to find even more optimal fabrication plans for a single metric. But we also want to show that exploring design variations can meaningfully improve a user's ability to find a fabrication plan at the right trade-off. We found that the design exploration leads to a wider diversity of plans. That is, more points in more places on the Pareto front. In many cases, each trade-off was only enabled by the underlying design, as evidenced by the variety of colors that contribute to the Pareto front. Here we show some of the design variations that enable very different trade-offs. We have the ability to search over a huge space of potentially unintuitive designs owing to our computational power. So we know that some of our solutions are non-obvious. To compare our results to a human baseline, we asked carpentry experts to generate design variations and fabrication plans for each model. Their solutions are plotted as diamonds. Since experts produce each solution by hand, they produce Pareto fronts with many fewer solutions than our approach. And for 14 of the 16 models, solutions generated by our tool dominate the expert solutions. And for the other 2, they were equally good. To test whether the bag of parts eGraph contributes towards our tool's performance, we compare against a nested optimization pipeline. The baseline approach invokes Carpentry compiler pipeline on each design variant that our tool explores, and then it takes a Pareto front across these design variations. The 2 methods achieve the same or even better Pareto fronts, but our approach is about 1 order of magnitude faster. Finally, we would like to show that our multi-objective, multi-level optimization algorithm is a general tool that is not restricted to woodworking. Here are 2 extensions with this goal in mind. First, our method naturally extends to other objective functions when extracting the Pareto front. Here we show one example where we were able to optimize a model considering stability as an additional objective, calculated with physical simulation. We were also able to successfully optimize a mixed material model that showcases our ability to handle such added design complexity. So we have shown some extensions of our design exploration approach, but there's still much more future work that we are excited by. One interesting direction for future work would be to support continuous variations in the design space. We are also interested in finding other good applications of the ICEE strategy. Another direction we are eager to explore is how to extract the Pareto front while considering other objectives such as ease of assembly or appearance. Finally, we would like to explore learning-based methods to speed up the extraction process. To conclude, to truly optimize a design for fabrication, you must optimize across multiple design variations. Fundamentally, this is a bi-level problem. With the insight that both design and fabrication plans are programs, we propose a novel solution to this very difficult search by extending results from the PL community. While we share our successes in carpentry, we believe that this is an interesting and reusable approach that extends to a variety of problems in computational design and beyond. Thank you.